Dear students, welcome to Sia's digital classes. Today let us learn the concepts of addition theorem and multiplication theorem in probability. So first let us deal with addition theorem. So here is an addition theorem. Addition theorem, to know that we have two different cases. So addition theorem is different from mutually exclusive and non-mutually exclusive events. So to know that probability and all, first we discussed small definitions, that is mutually exclusive, non-mutually independent events, equally likely events. Those are all the situations for how the outcomes will be. So based on that situations, we'll define our addition theorem also. So here two types will arise. One is mutually exclusive and another is non-mutually exclusive. So first mutually exclusive, let us discuss here. First, to know that what is mutually exclusive, we need to understand properly. Like mutually exclusive means, for example, if you take tossing of a coin. So whenever you toss a coin, what happens? Its result is either you get a head or you get a tail, isn't it? So only two results are there, either head or tail. Suppose if I have tossed a coin, I have got a head as my result. So what happens? Is there any chances for a tail to occur? No, no. Head has occurred, the final result is head itself. So their head and tail are mutually exclusive. Head appeared, finish. There is no other possibility to get tail. So mutually exclusive. One to one, there is only one possibility. One appears, the other doesn't have any chance to appear. So head has appeared, that's it. Tail doesn't have any option to get as a result. If you want, you can try one more. Again, you take a coin and toss and then check it out whether you are getting head or tail. But in first itself, both will not come as an outcome. So such situations will call as mutually exclusive events. So for such situations, let us check it out how the addition theorem goes on. Addition theorem in the sense, whenever two possibilities are there, like two results you want to check, or more than the two results, where one to one they are related, unions whenever it will frame, at that time we'll go for addition theorem. So let us check it out for mutually exclusive events. So when A and B are two mutually exclusive events, so A and B, some cases we are considering, and both are mutually exclusive. That is, both cannot occur at the same time. That's what we discussed, right? So one appears, the other doesn't have any chance to appear. So then the probability of occurrence of A or B is equal to the sum of their individual probabilities. So what happens in such situations? If you take their unions, it has to go for individual additions. So like P of A union B, if you consider, check it out through formula, let us discuss. So probability of A or B, one occurs, the other doesn't have. So A or B, any one will appear. So what happens is its formula goes to P of A plus P of B. Individual values you have to sum up. So that becomes your mutually exclusive formula for addition theorem. So symbolically, OR means union. You have to consider you might have learned in school and all, intersections, unions. So whenever OR is there, that goes to union. Whenever AND is there, that goes to intersection. So intersections we learn in multiplications, unions we learn in addition theorem. So our addition theorem for mutually exclusive cases, probability of A union B is equal to probability of A plus probability of B. So that is your formula for addition theorem. Now let us check it out. Diagrammatically, it can be represented as A set, B set. Mutually exclusive we have discussed, right? Means one is nothing to do with the other. So diagram, what we have done, separately we have taken A, B. They are not even nearby. They are completely separate. So A has nothing to do with B. A, if you consider, B you can't consider at all. For that, separate diagrams we considered. So that is what we call mutually exclusive events. Now, mutually exclusive for three cases. The same thing when three cases are there. How the formula goes on, let us check it out. So, probability of A or B or C. Three cases, right? So, A or B or C, if you consider, symbolically, A union B union C is equal to simply the same formula extended with the C part. Means P of A plus P of B plus P of C. So this is your formula for mutually exclusive when we have three events in our hand. So for 3 events we discussed addition theorem now. Now let us discuss same addition theorem for non-mutually exclusive events. Now what is non-mutually? Mutually just now we discussed, right? Its opposite is non-mutually. Means mutually what we discussed, tossing of a coin, if you consider head appears, there is no way chance to get tail as a result. One appears, the other doesn't have any chance, isn't it? Now non-mutually means there is every possibility to get both the outcomes as a result. Like one of the example here we discuss, check it out. If you consider a pack of cards, so cards will be playing cards, so 52 cards will be having. There in such situations where many possibilities are there, you may get a non-mutual possibilities also. Means like I want a red card and that should be a queen card. Is there any possibility? Yes, definitely. Two conditions I'm mentioning, red card and it should be a queen card. So red color, two types we have, that in that two reds any one of the card can be a queen card. So both the possibilities at a time I'm getting. So non-mutual exclusive, both the possibilities at a time you may approach. So for such situations, how the addition theorem goes on, let us check it out here. So in case of non-mutual exclusive events, if the events occur together, this is a variation in the addition theorem. So whenever non-mutual cases are there, how the formula changes, they are giving here. So when A and B are non-mutual exclusive events, then the probability of occurrence of A or B is the sum of their individual probability, which should be deducted from the probability of A and B. So what they are telling in the definition, so whenever non-mutual cases will be there, means at a time two results you may get. In such situations, both together intersections whenever possible, that intersections you have to remove from that all possibilities. So how the formula goes on here is A union B is equal to A or B, nothing but A union B is equal to the both the values will be adding, that is for mutually we have discussed already. So add both of the possibilities, individual possibilities, add them, then subtract wherever their intersections are possible. Means we have to subtract the both together whatever the approach we are getting. The same card, like toss card, taking out a red card which is a queen card, I'm telling, right? So both at a time whatever possibilities are there, that you have to subtract from the formula. So this becomes your addition theorem formula for non-mutual exclusive cases. So here diagrammatically also they have explained. Let us check that also once. So here we have the diagram. So what they are related to each other. Mutually exclusive means non-mutually exclusive means both can appear. So what we have done, diagrams we wrote together. Both the circles we have got intersections because there is a possibility to both the cases to appear as a result. So first circle, second circle we mixed up. So in between whatever the lines you got, that is your intersection parts. Both happens together. So A intersection B we call. So that's what is your non-mutual exclusive. Okay. So for that the same formula whenever non-mutual cases are there for 3 different events or 3 different outcomes, what could be the formula, that also they have given here. Let us check it out. That P of A or B or C, nothing but A union B union C goes to the formula, same formula what we just discussed. Up to here we discussed, right? P of A plus P of B, C was not there, so it doesn't have. So minus probability of A intersection B was there. Now the third event also included. So plus P of C minus P of A intersection C. A with the combination of C you have to subtract. Now B with the combination of C also you have to subtract. So A intersection C and B intersection C we have subtracted, and one more possibility also will be there whenever three events are there, that is all the 3 intersections, all the 3 possibilities, that you have to add up here, not the subtraction, you have to add up. So probability of A intersection B intersection C is added to the formula. So this is your non-mutually exclusive formula for 3 events. Now let us discuss for multiplication theorem. So multiplication theorem, it goes like this. If A and B are two independent events, check it out, the word independent. So whenever events are independent, then only multiplication theorem will hold good. So now let us try to learn what is independent event. So independent means one result has nothing to do with the other result. It will not depend on each other. So like tossing of a coin, again if you consider, toss a coin, whatever the result you will get, that is nothing to do with the another one. Head is a result. Head is not we got as an answer because of tail. That the tail impact is not there on head. Simply we have tossed and we got result as head. So tail did not influence our head to get as a result, or head did not influence tail to become its as an answer. So such events will call as independent, not related to each other. No one will influence the other. Whatever the approaches are there, simply we'll get that as an answer. So that those are independent events we'll call. So such events are there, then we'll go for multiplication theorem. So here A and B are two independent events, then the probability of occurrence of both the events is equal to the product of their individual probabilities. So whenever two independent events, if you consider, its result is its multiplication they are telling. So nothing but formula wise, probability of A intersection B goes to P of A into P of B. That is your multiplication formula whenever two events are there. Similarly, when three events are there, one more formula will get the same what we discussed right now, the same thing. Probability of A intersection B intersection C is equal to all three multiplications you have to consider, that is P of A into P of B into P of C, and so on. So on means 4 events, 5 events, 10 events, whatever, you have to go on multiplying to each other. So that is your multiplication theorem. Now let us discuss one example under that, the conditions also is there for multiplication, that also let us discuss first. So if A and B are two dependent events, so here dependent events they are telling. So dependent events, I said independent events, for that multiplications will get. So whenever independent events are dependent events are there, what to do? Let us check that now. In such a case, multiplication theorem is altered. Means we'll make little changes with the multiplication theorem, and then in the formula we'll make the changes, and then we'll try to get for dependents the events also. So what are the changes? Let us check it out. So probability of A intersection B goes to P of A into P of B, we discussed already, right? Whenever independent events are there. Now for dependent event, what happens is P of A instead of P of A, P of B as it is, what we do is P of B by A. So B is dependent on A. If A comes, then only B will come. In like such situations are there, means we'll go for dependent event. So formula changes like this. Probability of B by A into P of A means here what happens where P of A given B or A by B, anything we can call. So P of A by B is a conditional probability of A given that B has occurred. So the probability of occurrence of event A when event B has already occurred. So event B has already occurred. Using B, we are trying to find out A. So B is independent, it has already happened. A is dependent on B. In such situations, we will consider this formula. So we have got multiplication theorem formula for dependent and independent events both. Now let us check it out an example to get these formulas. So I am trying to get here using an addition theorem. So check it out the example. In a group of 60 students, 35 students can speak Hindi. So some students example we have considered. So some 60 students are there. Out of that, 35 can speak Hindi it seems. Next, while 25 can speak both Hindi and Telugu. So some 25 students can speak both the languages Hindi and Telugu. All the students can speak at least one language. So out of all like 60 students are there, everybody can speak at least one language, it seems. Now, how many students can speak Hindi but not Telugu? They are asking. So, only one language they can speak, that they are asking here. So, let us check it out the solution. So, first draw the diagram. It helps us to get our answers. So, first one, 35 we have considered here, n of a. N of a is nothing but. So, first let us deal this solution through a diagram. So, let A denote set of people who speak Hindi. So, B set of people who speak Telugu, they are telling. So, N of A who speaks Hindi, that is 35. So, first let us draw the diagram also. So, first circle is people who can speak Hindi. So, first circle 35 we considered. Then second circle those who can speak Telugu. So, that individually we want. So, keep that one. And then union, both union all together is 60 students. So, overall is 60 students we consider. Now, A intersection B also they have given, means both they can speak both the languages, 25 they have given. So, here 25 we got. So, only the Telugu speaking people we need as an answer. So, for that I have kept the question mark here, and this also how to get, let us discuss now. So, N of A or probability of A union B will consider addition theorem formula. So, N of A plus N of B minus N of A intersection B. Check it out. It's an addition theorem formula. So, all the values we have, simply substitute and try to get the remaining missing value. So, N of A union B they have given as 60. A union B is nothing but overall students, how many are there who can speak Telugu and Hindi, that is 60, plus N of A. N of A is nothing but Hindi speaking students, they have given already, that is 35, plus N of B missing as it is you write, minus 25 the intersection value. Now, variable we can't add, so take it to the other side, it goes to the next side, and 60 minus 35, 35 I am taking to the other side, 60 minus 35 as well as 25 also I am taking to the other side. So, 60 minus 35 minus goes to plus, plus 25. So, you got N of B as 50. So, here how we have got the answer, N of B is equal to 50. Now, what we have done, we have taken N of A minus B. So, addition theorem, if you consider addition theorem, here itself we got the answer, N of B as 50. Now, one more here, we need a Hindi speaking but not Telugu. For that, we have trying here to get, so N of A minus B, if you consider, you will get, so N of A minus N of A intersection B. So, N of A is 35 we have. So, 35 minus N of A intersection B, 25 you consider, your answer is 10. So, therefore, the number of students who can speak Hindi but not Telugu is 10 students. So, this is how we will try to get our result through the addition theorem. So, this diagram also will help us to get our answers properly. So, whenever you are trying addition theorem, go with the diagram also and use the addition theorem formula, you will get the answers in this way. Hope you have understood addition theorem and multiplication theorem in this session. See you all in the next session. Thank you.